In Chapter 8, we discuss magnetic materials and devices, starting with the physical origin of magnetism and the different types of magnetic materials, then the microstructure of magnetic domains, and finally the uses of hard and soft magnets in devices. Ferromagnetic materials are essential components for electric motors in electric vehicles, magnetic memory, that is still the most widely used way to store computer data, and transformers, which are needed to convert and transmit electrical power. We start with briefly discussing the types of magnetism, keeping in mind that engineering interest is focused on what we colloquially call magnetic materials, as opposed to non-magnetic materials. The engineering and common use of the term magnetic refers to materials which have a visible attraction to a magnet due to a spontaneous magnetic moment, like iron filings in the tube here. In physics, we call this ferromagnetism, due to a material that is ferro or ferrimagnetic. Ferromagnets usually contain the elements iron, cobalt, or nickel, each of which are strongly ferromagnetic at room temperature in their pure metallic form. Many newer high-performance ferromagnets contain rare earth elements that contribute to the magnetism, such as neodymium iron boride. Non-magnetic elements have a magnetic response that is too weak to have much of an engineering use. These include materials containing non-magnetic elements, such as glass, polymers, air, or here, sulfur. Compounds with magnetic elements, such as iron sulfide, are also often non-magnetic. Even stainless steel is essentially non-magnetic, even though it is mostly a mixture of iron and nickel, which are both ferromagnetic in elemental form. In physics, such non-magnetic materials are classified by their microscopic response to a magnetic field as diamagnetic, paramagnetic, or anti-ferromagnetic. In material science, we will be mostly interested in ferromagnetic materials, but in order to explain the terminology, we will briefly discuss non-magnetic materials. Recall from physics that a moving charge produces a magnetic field according to the right-hand rule. When moving in a loop, it produces a uniform magnetic field that is perpendicular to the loop. Magnets are often described as magnetic dipoles because they act like the magnetic equivalent to electric dipoles, where north and south poles act like positive and negative charges for magnetic as opposed to electric field lines. Magnets only exist as dipoles. There is no magnetic equivalent of isolated charges that we have for electric charges such as electrons or protons. Recall also from physics that a magnetic field applies a Lorentz force on a moving charge, where both the force and field are perpendicular to the direction of the moving charge. Spin-paired electrons in atoms are akin to charges in a conducting loop. Classical magnetic induction suggests that applying a magnetic field induces electrons to move in a direction which produces an opposing magnetic moment. The direction of the electromotive force is given by Lenz's law, which states that an induced current will flow in the direction that will oppose the change which produced it. This effect is very small in materials unless the material is superconducting. In the lab, we apply a magnetic field with an electric current that we call the magnetizing field H. This magnetizes a material inside the coil with a magnetization M. The resulting internal magnetic field that the atoms in the material feel is the B field, which includes contributions from the applied magnetizing field H and the magnetization of the material M. In the diamagnetism example, the induced magnetic moment M opposes the applied magnetizing field H and is much smaller than H. Magnetic susceptibility is most commonly used to describe non-magnetic materials. The definition and usage of magnetic susceptibility and magnetic permeability is similar to what we used for electric susceptibility and permeability. But since the magnetism of non-magnetic materials is not used in many devices, We will focus only on the qualitative aspects for this class. A diamagnetic material, for example, with induced magnetic moment opposing the applied H field, has a negative magnetic susceptibility. Although all atoms have a diamagnetic response, it is very small. Some atoms have an intrinsic magnetic moment caused by the spin angular momentum of the electron. The magnitude of the magnetic moment is given by the charge of the electron minus E divided by the mass of the electron and the angular momentum due to the spin. In principle, the orbital angular momentum of the atom can also produce a magnetic moment. But in solids, this angular momentum is usually quenched, so only the spin contributes to the magnetic moment. An atom with one unpaired electron, for example, will have spin 1/2. That means, from quantum mechanics, the angular momentum will precess about a given direction, say z defined by the direction of the applied magnetic field, so that the z component of the angular momentum is h bar over 2. This leads to a magnetic moment from a spin 1/2 electron of E h bar over 2m, which is the smallest quantum limit magnetic moment that we call the Bohr magneton. A magnetic moment in an external magnetic field experiences a torque to align it with the field. This can be described with the magnetic potential energy, where, for example, an electron spin aligned with a magnetic field has a lower energy than one opposing the field. The quantum mechanical representation is that when there is no magnetic field, B equals 0, each electron state can have a spin up and spin down electron with the same energy, represented as two degenerate states. When a magnetic field is applied, the degeneracy is broken and the two states separate in energy, the spin aligned state reducing its energy and the opposite spin state increasing in energy, where the difference in energy is 2 Bohr magnetons times the magnetic field for spin 1/2 electrons. Recall that in metals, electrons can be described by extended wave functions forming bands. We said that each wave function could have 2 electrons. That was for spin up and spin down electrons. If we plot the density of states of spin down electrons on the left and spin up electrons on the right, the density of states would be symmetric, and we would fill the same number of spin down as spin up electrons in these states up to the Fermi level. The resulting metal has all the spins paired, meaning 0 net magnetic moment. When a magnetic field is applied, the spin parallel states are reduced in energy, while the spin opposite states are increased in energy. Some spin down electrons will flip their spin to align with the magnetic field, setting a uniform Fermi level for both spins. This will lead to a small but non-zero net spin up and a non-zero magnetization of the metal in the direction of the magnetic field. We call this positive magnetic susceptibility observed in metals polyparamagnetism. Although non-zero, it is too small to observe without sensitive instruments, so that most metals, like aluminum, are considered non-magnetic. When unpaired electrons are localized on atoms, as happens in many insulators, the atoms have a permanent magnetic moment due to electron spin. Often the interaction with other atoms is so weak that the magnetic moment points in random directions that fluctuates due to random thermal agitation, such that there is no net magnetic moment. In the presence of an external magnetic field, the magnetic moments are preferentially aligned, even with the thermal agitation, and a small magnetization in the direction of the field results. Stronger fields and lower temperature lead to more alignment, so that the net magnetization is well described with a temperature-dependent magnetic susceptibility. To summarize, non-magnetic materials have a small, not very useful magnetization when placed in a magnetic field that can be described with a magnetic susceptibility chi, where magnetization is directly proportional to the applied field H. Unpaired electrons in insulators have a magnetic moment from the electron spin. They are randomly oriented due to thermal agitation, but can be somewhat aligned with an external magnetic field. This produces a positive magnetic susceptibility we call paramagnetism, that is greater at lower temperature when the thermal energy is less. In metals, only a few electrons at the Fermi level flip spins to align with an applied magnetic field. Since the net magnetization is aligned with the field, we call it a type of paramagnetism, but is temperature independent. Even atoms with paired spins have a very small diamagnetic response, regardless of temperature, meaning a small m opposing the magnetic field from all materials that is constant with temperature. When there are atoms with magnetic moments due to unpaired spins close to other such atoms, they can interact with the neighboring magnetic moments to align them. When the interaction favors parallel alignment, the material is a ferromagnet. A ferromagnet has a spontaneous magnetization, meaning no external field is needed to produce a net magnetization. Elemental iron, cobalt, and nickel have partially localized d electrons with unpaired spins that provide the large magnetic moment, even though they are metals. Nickel-iron alloys, called permalloy, are commonly used in transformers to change voltage for power transmission and electronics. The interaction with neighboring atoms can also be such that it aligns them antiparallel instead of parallel. When the interaction favors antiparallel alignment, such that the magnetic moments exactly cancel, the material is called an antiferromagnet. An antiferromagnet has no spontaneous magnetization, m equals 0, and considered non-magnetic. In a magnetic field, an antiferromagnet has only a small paramagnetic response. Elemental chromium has partially localized d electrons with unpaired spins, but the magnetic dipoles are oriented so that they exactly cancel. Antiferromagnetic interaction can also lead to a ferromagnet when the two antiferromagnetic sublattices don't exactly cancel. The resulting net magnetic moment has nearly the same ferromagnetic properties as a material with ferromagnetic interactions. The most common ferromagnets used commercially are actually nonmetallic ferrimagnetic oxides called ferrite. They contain iron in the 2+ and 3+ oxidation state with several unpaired electrons that produce a localized magnetic moment. Magnetite, for example, is a naturally occurring magnetic mineral of iron oxide, Fe3O4, and various impurities needed to make it a permanent magnet. Mixing iron ferrite with other elements leads to ferrites with different magnetic properties, making it useful for a variety of applications.